Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's lecture is a brief introduction to Programmable Logic Controllers, or PLCs. Our objective is to describe the main parts, purpose, and function of a PLC and introduce some general concepts common to most PLCs. Though the scope of this lecture is introductory in nature, pay close attention to the terms employed and defined, since they will be routinely employed across a broad spectrum of later applications. If at any point in your education you wish to come back and review this core introductory material, that option is available and encouraged. As we've previously discussed, logical operations of immense complexity can be created by hardwiring input devices, relays, and output devices in a prescribed fashion. The classic example is the logical AND operator formed by the series connection of two normally open contacts. Contact 1 and Contact 2 must both close to assert the output. In contrast, the logical OR operator is formed by the parallel connection of two normally open contacts. Either Contact 1 or Contact 2, or both of them together, can close to assert the output. Traditional hardwire relay-based ladder logic, however, is progressively being replaced with reprogrammable devices known as Programmable Logic Controllers, or PLCs. A PLC is essentially a ruggedized computer designed to operate in an industrial environment characterized by wide ranges of humidity, particulate contamination and temperature, electrical noise, unclean power, and higher voltages. PLCs are designed to replace hardwired relay-based ladder logic because they are more reliable, flexible, cheaper, faster, can communicate more effectively, and perform advanced data processing functions. PLCs differ from normal computers in that they are designed to run a single program in a stepwise or sequential fashion. The reliability and flexibility of a PLC stem from the fact that they are reprogrammable devices. Programming prevents errors due to miswiring, and the devices can be reprogrammed without rewiring. This is a major time and cost savings advantage. Consider the labor involved in converting our previous hardwired AND operation into a hardwired OR operation. This would necessitate a technician physically removing one wire and adding two more. Imagine if this was just one of 100 similar systems necessitating the same modification. Compare and contrast the ease if all 100 systems could simply be reprogrammed over a communications network at the push of a button to perform the OR function without the expensive and time-consuming requirement of physically rewiring it. In addition to these advantages, PLCs are designed to facilitate troubleshooting with diagnostic tools. Depending upon the degree of complexity, PLCs can generate reports, log faults, and technicians can simulate and run the program line by line or force inputs and outputs. Although intended to replace traditional hardwire relay-based ladder logic, PLCs are still often programmed using methods astoundingly similar to ladder logic. Here are two PLC programs executing the two-input AND and the two-input OR function using a graphical programming method called relay ladder logic. The similarities between this programming method and traditional hardwire relay-based ladder logic are obvious. Other programming methods include graphical means like function block diagrams or textual ones like structured text. Regardless of the methodology employed, the purpose of a PLC, like traditional hardwire relay-based ladder logic, is to control and coordinate a larger system by starting, stopping, and changing the direction of actuators like electric motors and hydraulic cylinders. Additionally, PLCs can modify and manage actuator output characteristics like varying the rotational speed and torque of an electric motor or the extension and retraction force and speed of a hydraulic cylinder. Finally, systems employing PLCs can perform additional functions like counting, timing, comparison, arithmetic, and data processing functions. PLCs are rated by memory and input and output capacity and format, whether they're fixed or modular and expandable, as well as the different types and number of available programming instructions. PLCs, in addition to coordinating and controlling a single process, can also be used to coordinate and control and communicate with other PLCs. A PLC is characterized by several parts, notably the CPU, inputs, outputs, a communication port, power supply, a chassis, and a reprogramming device. The CPU is the brains or memory of the PLC, and it is the portion that evaluates the state of the inputs, outputs, and other data and executes the program. The input is the interface between the PLC and remote or field input devices like switches or sensors. The input conditions and isolates the input signals from the internal and the output signals. The output is just the opposite. It is the interface between the PLC and field output devices like the coils of contactors or solenoid-operated hydraulic valves. The output conditions and isolates the output signals from the input and internal signals. The chassis is the housing of the PLC, which could either be modular or fixed. The power supply is the DC or AC input necessary for operation. The communication ports allow the PLC to send and receive data, as well as allow other devices to monitor and control the process. Input or output could therefore be local or at the point of use of the PLC, or remote, meaning these signals come from a different place via the communication port. Delivery of remote inputs and outputs via the communication ports saves the necessity of multiple long wire runs. A PLC can be reprogrammed via manual entry, a handheld device, or a PC in a communications link. Input or output from a PLC can either be DC or AC. Common flavors of pilot level voltage include 24-volt DC and 120-volt AC, with a progressive movement towards devices favoring the safer 24-volt DC requirement. Field inputs and output devices must be compatible with the PLC's operation voltage, and if not, necessitate the use of interposing relays that translate one voltage flavor to the other. As the name implies, an interposing relay simply interfaces the two different voltage schemes. Input and output signals are conditioned by the input and output modules by enforcing minimum trigger levels, filtering electrical noise, and debouncing switched input. Sometimes this is done by using optical isolators, devices that link the PLC CPU to the input and output modules using light only. Output mechanisms can take the form of electromechanical relays with moving parts, or solid-state devices with no moving parts like transistors or triacs, depending upon the characteristics of the field output devices. Input or output from a PLC can either be digital or analog in nature. Digital signals have two mutually exclusive states, off or on, with no intermediary between states. A pressure switch would be an example of a digital input in that it sends a clear closed or a clear open signal to the PLC. A contactor coil would be an example of a digital output in that it requires a clear on or a clear off signal from the PLC. The contactor, based on the state of the PLC output, would either be open or closed, and never a little bit of both. An analog signal, in contrast, is one that is continuously infinitely variant inside a given range. A pressure sensor would be an example of an analog input in that it sends a proportional electrical output based on input pressure. More pressure results in more voltage. This analog signal can be analyzed by the CPU, and the PLC respond appropriately to pressure conditions inside a specific range. A variable solenoid for a hydraulic proportional valve would be an example of an analog output, and that movement of the spool varies in proportion to the electrical output. More voltage output means more movement of the spool and consequently more flow. The analog nature of the output signal would allow an appropriately proportionate response for a given input condition. There are a number of different confusing schemes used to classify PLCs. However, I split them into two very large general categories. PLCs can either be fixed or modular. Small-sized, basic fixed PLCs are often self-contained standalone units, sometimes incorporating the power supply, input and output modules, CPU, and any communication ports into one integrated package. These devices may or may not be expandable with expansion modules. Small-sized, basic fixed PLCs are ordinarily very inexpensive, however limited in functionality, and are best suited for less complex applications. These devices are known alternatively as programmable logic relays, or PLRs, intelligent relays, smart relays, logic modules, or other manufacturer-specific terminology. Examples of small-sized basic fixed PLCs include the TECO SG2 PLR, the Easy Intelligent Relay family, Siemens Logo logic modules, and the Allen Bradley Pico or Micro Programmable Logic Controllers. All these manufacturers offer variants within these families with different characteristics, like supply voltage and number and type of inputs and outputs, depending upon application. These devices can be programmed via manual entry on a ridiculously small screen, or via a communications link in a PC running manufacturer-specific programming software. Some manufacturers offer fully functional programming software for free. Other manufacturers may require purchase of the programming software. The fully functional programming software allows a user to create and simulate a program, as well as download it to an actual device and sometimes monitor the process online. Other manufacturers offer demo and simulation programming software for free and necessitate the purchase of software to program and monitor an actual device. Later lectures will take a closer look at some of these small basic fixed PLCs and programming software.